Hello there, and welcome to Science Documentary for Sleep. Tonight, I'll be spending some unhurried time with the very small subject atoms and the surprisingly steady role they play beneath everything familiar. This is a documentary in the simplest sense, a calm walk through established science, spoken slowly enough to let images form before explanations settle in. You're welcome to listen closely, or loosely. Nothing here needs to be memorized, and nothing is being tested. Understanding can arrive gradually, or not at all, and both are fine. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. If you feel like it, you can also share where you're listening from and what the local time is for you. I'll be here either way. Let's begin. We begin from the gentle orientation already in place, without adding pressure or momentum. The idea of atoms has been quietly introduced, not yet examined, simply present. It can help to picture a familiar object nearby, a table, a cup, a wall catching light. Nothing special, just something solid and still. Let it remain as an image, without analysis. The core fact to hold here is simple and well established. All ordinary matter is made of atoms. Every solid, liquid, and gas you encounter is composed of these extremely small units. They are not metaphorical building blocks, they are literal ones, described precisely by physics and chemistry. To clarify gently, this does not mean atoms are the smallest things that exist. It only means they are the smallest units that still retain the identity of a chemical element. Break them further, and the material changes category. This matters because it gives matter a shared structure. Differences in appearance do not imply different foundations. As an observer, you are surrounded by this common architecture at all times. You don't need to examine it further yet. The idea can remain where it is, settled but open. With that foundation resting quietly, the image of matter can soften without disappearing. The table, the cup, the wall are still there, unchanged. Now imagine slowly zooming in, not with speed, but with patience. Layers of surface detail fade away, leaving structure beneath. The central fact here is this: atoms are extraordinarily small. A single atom is typically around 1/10,000,000th of a meter in diameter. To put it plainly, millions of atoms can fit across the width of a human hair. This scale is difficult to visualize because it sits far outside everyday experience. Our senses evolved for survival at human size, not for direct awareness of atomic dimensions. The significance is subtle but important. Because atoms are so small, matter appears continuous to us. Surfaces feel smooth even though, at atomic scale, they are structured and discrete. You move through a world that feels solid because your senses average over vast numbers of atoms at once. That averaging is effortless. You don't have to notice it. The mind can rest while scale quietly expands. As scale stretches further, the idea of size naturally invites a question about quantity without needing to ask it directly. Picture a single grain of sand held between your fingers. It feels simple, singular, almost minimal. The factual insight here is that even tiny objects contain enormous numbers of atoms. A single grain of sand contains on the order of a quintillion atoms, that is, a 1 followed by 18 zeros. This number is not an estimate meant to impress. It arises from measured atomic masses and known volumes. Physics arrives at it calmly, through arithmetic, not wonder. The importance of this lies in reliability. When scientists talk about atomic behavior, they're often describing patterns that emerge from unimaginable numbers acting together. From your perspective, you never encounter individual atoms directly. You encounter collectives so large they behave smoothly and predictably. It's enough to let that abundance exist without trying to grasp it fully. The number does not need to be held tightly to be true. Large numbers tend to blur into abstraction, so it can help to return briefly to structure. The grain of sand remains, but attention shifts inward again. Imagine that each atom within it is not a solid bead, but something more open, more spacious. The key fact here is that atoms are mostly empty space. An atom consists of a tiny, dense nucleus surrounded by electrons that occupy regions far away by comparison. If an atom were expanded to the size of a stadium, the nucleus would be closer in size to a small marble at the centre. This does not mean atoms are flimsy or unreal. The emptiness is governed by electromagnetic forces that give matter its stability. Why this matters is quiet but profound. Solidity is not the absence of space, but the balance of forces within it. You feel firmness not because matter is packed tight, but because atomic structures resist overlap. That resistance works continuously, without effort, allowing the idea of emptiness to sit calmly beside the feeling of solidity. With that openness in mind, the nucleus becomes easier to notice, even if only as an idea, not visually, but conceptually. Picture a calm centre, dense and steady, holding most of the atom's mass in one place. The factual focus here is that nearly all of an atom's mass is concentrated in its nucleus. Protons and neutrons reside there, while electrons contribute very little to the total mass. This distribution was not assumed. It was discovered through careful experiments in the early 20th century, where particles were scattered and their paths observed. The consequence of this arrangement is stability. Mass anchors atoms, while electrons determine how atoms interact chemically. Each part has a distinct role. From where you are, this division works invisibly. You never feel nuclear mass or electronic structure separately. They cooperate silently, allowing matter to behave consistently enough that you rarely have to think about it at all. As structure becomes clearer, differences between atoms can be introduced without urgency. The idea of sameness begins to share space with variation. Imagine a quiet library shelf where books share size and shape but differ in content. The single fact here is that each chemical element is defined by the number of protons in its atoms. Hydrogen has 1 proton, carbon has 6, oxygen has 8. This count determines an atom's identity, regardless of other details. Neutrons may vary, and electrons may be gained or lost, but the proton number remains the defining feature. Change it, and the element changes entirely. This matters because it gives nature a simple sorting principle. The periodic table is not arbitrary. It reflects this underlying order. As an observer, you live among combinations of these identities, woven together into materials, air, and living tissue. You don't need to memorize numbers. The stability of identity itself is the point worth letting linger. With identity now established, the presence of atoms can feel less abstract and more quietly personal. Not intimate, just near. Picture your own hand resting in space, warm, solid, unremarkable. The core fact to rest with is that the atoms in your body are not permanent residents. Over time, many of them are replaced through breathing, eating, and natural biological processes. The carbon, oxygen, and hydrogen atoms that make you upcirculate through the environment. This does not erase continuity. Structure and pattern persist even as components change. The significance is gentle rather than philosophical. Matter participates in cycles without losing coherence. You, as an observer, are part of those cycles without needing to manage them. For now, it's enough to let the idea remain unfinished, moving quietly forward as we continue. The sense of continuity from the previous segment remains, with atoms already established as stable yet circulating participants in the world. Nothing new needs to be added to that picture yet. You might imagine the same environment as before, unchanged, but now seen with slightly softened edges, as if attention is resting rather than probing. The factual idea here is that atoms are remarkably durable. Under ordinary conditions, atoms do not wear out, decay, or age. A carbon atom today behaves the same way it did billions of years ago. Its properties are fixed by its internal structure. This durability is not philosophical, it is measured. Atoms can participate in countless reactions without losing their identity. Why this matters is practical. The reliability of atoms allows chemistry, biology, and materials science to function predictably. Stability makes complexity possible. From your position as an observer, you benefit from this constancy without noticing it. Matter behaves tomorrow as it did yesterday. That steadiness can simply be acknowledged, then allowed to fade gently into the background again. With durability resting quietly in mind, attention can shift from longevity to motion without changing scale. Picture a calm room that appears still, even though air circulates slowly and continuously within it. The single fact here is that atoms are always in motion. In solids, they vibrate in place. In liquids, they slide past one another. In gases, they move freely and rapidly. This motion increases with temperature and slows as temperature drops. This behavior follows directly from thermal energy. Motion is not optional. It is inherent whenever atoms possess heat. The importance of this lies in explanation. Many everyday phenomena, expansion, diffusion, pressure arise from atomic motion rather than visible movement. You do not feel these motions individually. They average out, producing smooth experiences like warmth or stillness. It's enough to let the idea of constant motion exist quietly without trying to track it. Motion naturally brings atoms into contact, and contact introduces interaction without needing to force the connection. Imagine gentle collisions, like grains of pollen drifting and bumping in water. The core fact here is that atoms interact primarily through electromagnetic forces. These forces govern attraction and repulsion between charged particles, especially electrons. They determine how atoms bond, repel, or remain separate. This interaction does not involve physical touching in the everyday sense. It is force-based, acting across tiny distances. The significance is foundational. Chemistry, material strength, and biological structure all emerge from these electromagnetic interactions. From your perspective, this invisible force network produces tangible outcomes: hardness, flexibility, texture. You never perceive the forces themselves, only their effects. That separation allows understanding to stay calm and unhurried. As interactions become familiar, bonds can be introduced without changing tone or pace. Picture atoms lingering near one another, not fixed, but not drifting apart either. The factual focus here is that atoms can form chemical bonds by sharing or exchanging electrons. These bonds create molecules, ranging from simple pairs to large, complex structures. The rules governing bonding are consistent and measurable. Bonding does not merge atoms into something vague. Each atom retains its identity while participating in a larger structure. This matters because it explains how complexity arises from simplicity. A small set of atomic types can produce vast chemical diversity. You encounter this diversity constantly in water, air, and living tissue without needing to track its origins. The idea of bonding can remain gentle, more like proximity than attachment, as attention continues forward. With molecules now quietly present, scale can expand again without effort. Imagine layers building, not stacked deliberately, but emerging naturally from repeated patterns. The single fact here is that large-scale structures are emergent results of atomic arrangements. Crystals, metals, and biological tissues gain their properties from how atoms are arranged, not from the atoms alone. No new forces are introduced at larger scales. The same atomic interactions simply repeat, producing new behaviors when combined in large numbers. The importance of this is explanatory. It allows scientists to connect microscopic rules with macroscopic outcomes. As an observer, you interact with emergent properties: strength, color, elasticity rather than atomic details. That separation lets understanding stay light, without requiring constant attention to underlying mechanisms. Emergence invites comparison, and comparison naturally leads to variation, still within the same framework. Picture two objects that look similar but behave differently under pressure. The factual idea here is that different atomic arrangements can produce dramatically different material properties. Carbon atoms, for example, can form both soft graphite and hard diamond depending on bonding structure. The atoms themselves do not change identity, only their connections do. This matters because it shows that structure, not substance alone, determines behavior. Arrangement carries consequence. You encounter this daily without naming it, trusting materials to act as expected. The mind does not need to hold the details. The principle of arrangement can remain quietly present. With variation acknowledged, the atomic picture feels complete enough to rest, without closing. Imagine the world as it appeared at the beginning, ordinary and intact, now subtly informed by what lies beneath. The core fact here is that atomic behavior is governed by probabilistic rules, not precise paths. At small scales, outcomes are described by likelihoods rather than certainties. This is a defining feature of quantum mechanics. This does not introduce chaos at human scale. Probabilities average out, restoring predictability. The significance is quiet reassurance. Uncertainty at small scales does not undermine stability at large ones. You live comfortably within that balance, never required to resolve it. For now, the idea can remain open, neither resolved nor questioned, as the discussion moves gently onward. The sense of balance from before remains in place, with probability resting quietly beneath predictability. Nothing needs to be corrected or emphasized. You might picture the same ordinary world again, familiar and reliable, even as its deeper rules stay softly out of sight. The central fact here is that electrons do not orbit the nucleus like planets around a star. Instead, their behavior is described by regions of probability called orbitals, which indicate where an electron is likely to be found. These orbitals are not paths or tracks. They are mathematical descriptions derived from quantum mechanics. This matters because it reshapes how structure is understood at the smallest scales. Atoms are defined by likelihoods, not miniature mechanical systems. As an observer, you never see orbitals directly. You see their consequences in chemical behavior and material properties. The idea does not need to feel intuitive. It can remain quietly accurate, even if the image stays soft and incomplete. With orbitals present as a concept, attention can settle briefly on shape without forcing visualization. Imagine faint clouds surrounding a central point, denser in some regions, thinner in others. The factual focus here is that electron orbitals have specific shapes and energy levels. These shapes, such as spherical or more complex forms, determine how atoms interact and bond with one another. Electrons occupy the lowest available energy levels first, following well-defined rules. These rules are consistent across all atoms. The significance lies in explanation. Orbital shapes help determine why certain elements react readily while others remain inert. From your perspective, this invisible geometry influences everything from rusting metal to breathing oxygen. You do not need to picture the shapes precisely. Knowing that structure exists is enough for now. As energy levels come into view, change can be introduced without disruption. Picture an atom receiving a small pulse of energy, like a quiet tap rather than a jolt. The single fact here is that electrons can move between energy levels by absorbing or releasing energy. When they absorb energy, they move to higher levels. When they release it, they fall back down, often emitting light. This process is discrete, not gradual. Electrons move in steps, not slides. This matters because it explains atomic spectra, or the unique light signatures used to identify elements in laboratories and distant stars. You may have seen these colours indirectly, in neon lights or fireworks, without knowing their source. The idea can settle as a calm exchange between energy and structure, without needing to follow each transition. Light now lingers naturally in the picture, not as brightness, but as information. Imagine faint lines of colour appearing against darkness, precise and repeatable. The factual insight here is that each element emits and absorbs specific wavelengths of light. These spectral lines act like fingerprints, allowing scientists to identify elements even across vast distances. This is not interpretive, it is measured repeatedly, with consistent results. The significance is expansive. Atomic structure allows humans to analyze stars, galaxies, and interstellar gas without direct contact. As an observer, you live under starlight already decoded by atomic behavior. You don't need to hold the scale of that reach. It's enough to know that small structures inform large understandings. From light, attention can return gently to matter itself, now informed by energy exchange. Picture atoms responding subtly to their surroundings, never rigid, never random. The single fact here is that atoms can exist in different energy states depending on their environment. Temperature, pressure, and radiation all influence how atoms behave without altering their identity. These changes are reversible under ordinary conditions. The atom remains the same element throughout. This matters because it explains adaptability. Matter responds to conditions while retaining stability. You experience this responsiveness as warmth, expansion, or change of state, without tracking atomic details. The idea can rest as a quiet flexibility built into the structure of matter. With environmental influence established, neutrality and charge can appear naturally. Imagine balance, then a slight imbalance, subtle but consequential. The factual focus here is that atoms can become charged by gaining or losing electrons, forming ions. This process does not affect the nucleus, only the outer electron structure. Charged atoms interact differently, especially in solutions and biological systems. The importance lies in function, electrical activity in nerves, muscle contraction, and chemical signaling all depend on ions. As an observer, your body relies on these charged particles constantly, without conscious awareness. The concept does not need to feel active. It can remain as background support, steady and ongoing. With charge quietly present, atomic behavior feels complete enough to pause, though not to conclude. Picture the earlier image of your hand again, unchanged, now subtly informed by motion, probability, and charge. The core fact here is that atomic rules remain consistent everywhere in the observable universe. The same behaviors measured on Earth apply in distant stars and galaxies. This universality is confirmed through observation, not assumption. The significance is calm continuity. Nature does not change its basic rules from place to place. You exist within that consistency, supported by rules that do not need supervision. For now, the idea can remain gently open, ready to carry forward without needing closure. The sense of universality remains quietly present, with atomic rules extending without interruption across space. Nothing needs to be reinforced yet. You might imagine a distant landscape, perhaps a plain under a dark sky, no different in substance from where you are now. The central fact here is that atoms were formed early in the history of the universe. After the universe cooled from its initial hot, dense state, protons and electrons combined to form the first hydrogen atoms. This process occurred hundreds of thousands of years after the beginning of cosmic expansion. This formation was not sudden, but gradual, governed by cooling temperatures and expanding space. Why this matters is foundational. Atoms did not appear late or locally. They are woven into the universe's earlier stable structures. As an observer, you're composed of matter whose basic units emerged long before planets existed. That long continuity does not require reflection. It can remain quietly in place as time stretches outward. With early atoms now present, time can continue forward without acceleration. Picture vast spans of darkness punctuated by slow, steady change rather than dramatic events. The factual idea here is that the first atoms were almost entirely hydrogen and helium. Heavier elements did not yet exist in significant amounts. The early universe was chemically simple. This simplicity was not a limitation. It was a starting condition shaped by physical laws and initial energy distributions. The importance of this lies in sequence. Complexity did not arrive all at once. It accumulated over time. From your position, surrounded by diverse materials, it can be enough to know that variety had a gradual beginning. The idea of simplicity preceding richness can settle without needing comparison or emphasis. As chemical simplicity rests in view, transformation can appear naturally. Imagine pressure building slowly at the heart of a forming star, unseen but steady. The single fact here is that new atoms are created inside stars through nuclear fusion. In stellar cores, lighter nuclei combine to form heavier ones. Releasing energy, this process produces elements such as carbon and oxygen. Fusion is not chemical bonding. It alters the nucleus itself, changing one element into another. This matters because it explains origin. Many atoms essential to life were forged under extreme conditions far from Earth. As an observer, the materials that make up your body were once part of stars, long before becoming part of anything familiar. The idea does not need to feel dramatic. It can remain as a quiet lineage stretching across time. With stellar creation in mind, movement can follow without urgency. Picture atoms drifting outward from an aging star, dispersing into surrounding space. The factual focus here is that atoms created in stars are released into space through stellar winds and explosions. Events such as supernovae scatter newly formed elements across vast regions of the galaxy. This dispersal is measurable and observable through spectroscopy and astrophysical models. The significance is distribution. Elements are not confined to their place of origin. They are shared widely. From your perspective, the atoms around you have travelled immense distances before becoming part of Earth. That journey does not need to be imagined in detail. The fact of movement alone is enough to carry forward. As dispersal settles, gathering can follow naturally, without contrast. Imagine diffuse clouds of gas slowly thickening, drawn together by gravity. The single fact here is that atoms can collect into new structures under gravitational influence. Over time, clouds of gas and dust form stars, planets, and other bodies as gravity draws atoms into organized systems. This process is gradual and ongoing throughout the universe. Why this matters is continuity. Atoms are not static remnants. They participate repeatedly in cycles of formation. As an observer on a planet, you live within one such gathering, stable enough to feel permanent. That stability can be acknowledged quietly, without needing to trace its full history. With planetary formation present, conditions can narrow gently without closing in. Picture a young planet cooling, its surface shifting slowly toward balance. The factual idea here is that atomic interactions determine the physical and chemical properties of planets. Atmospheres, oceans, and minerals arise from how atoms combine under specific temperatures and pressures. No new laws are required. Familiar atomic behavior scales upward into planetary environments. The importance lies in connection. The same rules governing small interactions shape entire worlds. You inhabit the outcome of those interactions daily, without needing to recognize their origin. The idea can remain steady, linking the very small with the very large. With scale now spanning from early universe to planetary surfaces, attention can pause without stopping. Imagine the present moment again, ordinary and unaltered, quietly supported by deep history. The core fact here is that atoms participate in long-term cosmic cycles. They form, disperse, gather, and reform across billions of years, without losing their fundamental properties. This cycling is not purposeful. It is a natural consequence of physical laws acting over time. The significance is endurance. Matter persists through change without needing direction. As an observer, you are temporally aligned within that cycle, supported but not defined by it. For now, the idea can remain open, ready to continue without needing resolution. The sense of long continuity remains in place, with atoms moving through time without haste or destination. Nothing from before needs to be restated. You might imagine a quiet planetary surface again, stable enough to forget its motion, even as deeper processes continue beneath it. The central fact here is that atoms obey conservation laws. In ordinary physical and chemical processes, atoms are neither created nor destroyed. They are rearranged into new configurations, but the total number of each element remains constant. This principle is verified repeatedly in chemical reactions and closed systems. It is not a metaphor, but a measurable constraint. Why this matters is grounding. Change does not imply loss or gain at the atomic level, only reorganization. As an observer, you witness constant transformation, burning, rusting, digestion without atoms disappearing. That steadiness can remain quietly present, supporting change without needing attention. With conservation resting calmly, change itself can be approached more closely without tension. Picture a slow reaction taking place, invisible but consistent, like metal gradually darkening over time. The single fact here is that chemical reactions involve the rearrangement of atoms into new molecules. Bonds break and form, but the atoms themselves persist throughout the process. Energy may be released or absorbed, but atomic identity remains unchanged. This matters because it defines chemistry as transformation rather than creation. New substances emerge without new atoms being introduced. From your perspective, everyday processes, cooking, breathing, decay are all expressions of this rearrangement. You don't need to follow each step. The principle of persistence is enough to let the idea settle. As reactions become familiar, rates can enter quietly, without urgency. Imagine two similar processes unfolding at different speeds, one barely noticeable, the other quick but controlled. The factual insight here is that the speed of chemical reactions depends on atomic collisions and energy levels. Temperature, concentration, and catalysts influence how often atoms interact effectively. This does not change the rules, only the pace at which outcomes appear. The significance lies in predictability. Reaction rates can be adjusted without altering fundamental behavior. As an observer, you benefit from this control in everything from food preservation to industrial processes. The idea of pace can remain gentle, more like timing than force. With timing acknowledged, balance can follow naturally. Picture a system where forward and reverse changes occur together, neither dominating completely. The single fact here is that many chemical systems reach equilibrium, where reactions continue in both directions at equal rates. At this point, overall composition remains stable even though atoms keep moving. Equilibrium is dynamic, not static. Motion persists beneath apparent stillness. This matters because stability does not require inactivity. Balance can exist alongside change. From where you are, many environments, oceans, atmospheres, living cells maintain equilibrium continuously. The idea can rest as a quiet coexistence of movement and steadiness. With equilibrium present, attention can narrow gently toward living systems. Imagine a cell as a calm enclosed space, busy but not chaotic. The factual focus here is that living organisms rely on precisely controlled atomic interactions. Metabolism, growth, and repair all depend on regulated chemical reactions governed by atomic behavior. These processes are not exceptions to physical laws. They follow the same rules as non-living systems. The importance lies in continuity. Life emerges from matter without requiring new principles. As an observer, your own biological processes operate continuously without conscious involvement. That quiet autonomy can be acknowledged without needing to explore its complexity. With life now in view, renewal can appear softly, without emphasis. Picture atoms moving through a cycle entering a system, participating briefly, then leaving again. The single fact here is that biological systems constantly exchange atoms with their environment. Breathing, eating, and excretion move atoms through organisms without fixing them permanently. Structure persists even as components change. This matters because identity in living systems is pattern-based, not material-based. Stability arises from organization. As an observer, you remain yourself even as atoms pass through you. The idea does not need to resolve. It can remain as a quiet observation of continuity through change. With biological exchange present, attention can widen again without returning to abstraction. Imagine the broader environment, unchanged, supporting countless such exchanges at once. The core fact here is that atoms move through interconnected cycles on Earth, including carbon, nitrogen, and water cycles. These movements link atmosphere, land, ocean, and living organisms. No atom follows a single path. Participation varies over time. The significance is integration. Separate systems remain connected through shared atomic movement. As an observer, you exist within those cycles without needing to manage them. For now, the idea can remain open, continuing forward without seeking completion. The interconnected cycles from before remain quietly active, with atoms moving through systems without pause or destination. Nothing needs to be reinforced yet. You might imagine the Earth again as a whole, not as a globe, but as a stable environment where exchanges happen continuously and without announcement. The central fact here is that atoms are conserved even during large-scale physical changes. When matter changes state, such as ice melting into water or water becoming vapor, the atoms involved remain the same. Only their spacing and motion change. This principle applies universally under ordinary conditions. Phase changes do not alter atomic identity. Why this matters is clarity. Dramatic visible change does not imply deep structural change. As an observer, you experience melting, boiling, and freezing as everyday events, without needing to account for the atoms involved. That constancy beneath change can remain quietly reassuring as attention moves forward. With phase change resting in view, structure can return gently, without narrowing focus too sharply. Picture atoms arranged loosely, then drawn closer together, then held in place. The factual idea here is that the physical state of matter depends on how atoms move and interact. In solids, atoms vibrate in fixed positions. In liquids, they remain close but mobile. In gases, they move freely and spread apart. No new atoms are introduced in these transitions, only energy levels and motion change. The significance lies in explanation. Familiar states of matter arise from consistent atomic behavior. From where you are, these states feel distinct and intuitive, even though their causes remain invisible. The idea can rest as a quiet alignment between motion and form. As motion becomes familiar again, boundaries can appear without sharp edges. Imagine a surface that feels solid, yet yields slightly under pressure. The single fact here is that atomic spacing determines material density. Materials with closely packed atoms are denser, while those with more space between atoms are less dense. This spacing is governed by forces, not by randomness. This matters because density influences buoyancy, strength, and structural behavior. As an observer, you rely on density constantly objects sink or float, support weight, or remain light enough to move. You don't need to calculate it. The outcome is enough to let the idea settle. With density established, resistance can be introduced quietly. Picture two materials under the same force, one bending, the other holding firm. The factual focus here is that material strength arises from atomic bonding and arrangement. Strong bonds and regular structures resist deformation, while weaker or irregular arrangements allow flexibility. Strength is not a property added later, it emerges directly from atomic interaction. The importance lies in reliability. Structures hold because atoms interact consistently. From your perspective, this reliability allows trust in tools, buildings, and surfaces. That trust does not require awareness, it can remain as background certainty. With strength resting quietly, failure can appear without alarm. Imagine a crack forming slowly, not suddenly, under repeated stress. The single fact here is that material failure occurs when atomic bonds are overwhelmed or rearranged. Fracture, fatigue, and wear involve changes in bonding rather than disappearance of atoms. Atoms persist even when structures break. This matters because breakdown is structural, not fundamental. Damage rearranges matter without erasing it. As an observer, you encounter wear and decay as normal processes, not exceptions. The idea can remain neutral, neither reassuring nor concerning, simply descriptive. With failure acknowledged, repair can follow gently without contrast. Picture atoms settling into new arrangements after disruption. The factual idea here is that many materials can partially restore structure through atomic reorganization. Processes like annealing in metals allow atoms to move into lower energy configurations, improving strength. This is driven by energy input and time, not intention. The significance is adaptability. Matter can respond to stress by reorganizing within its rules. As an observer, you benefit from materials designed to recover or stabilize after strain. That recovery does not need to be followed closely. The principle alone can remain. With adaptation now present, the atomic picture feels broader without becoming heavy. Imagine everyday objects again, unchanged in appearance, quietly supported by the behaviors described. The core fact here is that macroscopic reliability emerges from microscopic consistency. The predictability of large systems depends on the regular behavior of atoms acting together. This connection is continuous, not layered. There is no clear boundary between atomic and human scale. The significance is coherence. The world holds together because its smallest parts behave steadily. As an observer, you move within that coherence without needing to confirm it. For now, the idea can remain open, steady enough to carry onward without closing. The sense of coherence from before remains intact, with large-scale reliability quietly supported by small-scale regularity. Nothing needs to be reinforced or contrasted. You might picture a familiar environment again, a room, a street, a landscape unchanged, dependable, and unremarkable in the best way. The central fact here is that temperature is a measure of average atomic motion. When something is warm, its atoms are moving more vigorously on average. When it is cold, their motion slows. This is not a metaphor. Temperature directly corresponds to kinetic energy at the atomic level. Why this matters is clarity. Heat is not a substance added to matter, but a description of motion already present. As an observer, you experience warmth and cold as sensations, not as moving particles. That translation from motion to feeling happens automatically, allowing the idea to remain calm and unforced. With temperature resting quietly, flow can enter the picture without urgency. Imagine warmth spreading slowly across a surface, evening out differences without direction. The factual idea here is that heat moves from regions of higher atomic motion to lower atomic motion. This transfer continues until temperatures equalize. This process follows consistent physical laws and does not require intention or guidance. The significance lies in predictability. Heat flow explains cooling, warming, and thermal balance in everyday situations. From your position, this process is constantly at work. Rooms equalize, objects cool, bodies maintain balance. You don't need to follow the movement. The result is enough to let the idea settle gently. As heat flow becomes familiar, limits can appear softly, without pressure. Picture a process that always proceeds in one general direction, even if slowly. The single fact here is that atomic motion underlies the concept of entropy. Entropy describes the tendency for energy to spread out and for systems to move toward more probable arrangements of atoms. This does not mean disorder in a casual sense. It means likelihood at the atomic level. This matters because it explains why certain processes are irreversible. even though atomic laws themselves are time-symmetric. As an observer, you encounter irreversibility constantly. Cooling happens, but spontaneous reheating does not. The idea can remain descriptive without needing interpretation or emphasis. With probability and direction now present, time can enter gently without expanding too far. Imagine change unfolding steadily without a preferred pace. The factual focus here is that many physical processes reflect statistical behavior of enormous numbers of atoms, while individual atomic motions are unpredictable. Large groups behave in stable, measurable ways. This statistical regularity is why physical laws appear smooth at human scales. The importance lies in reliability. Predictable outcomes emerge from unpredictable components. From your perspective, this allows trust in clocks, engines, and natural cycles. You're not required to reconcile the scales. The consistency alone is enough to carry forward. With statistics resting quietly, boundaries can soften again. Picture a container holding a gas, invisible yet present everywhere inside. The single fact here is that gas pressure arises from atomic collisions with surfaces. Countless impacts of atoms against container walls produce measurable force. No single collision matters. Pressure emerges from the total. This matters because it connects invisible motion to tangible force. As an observer, you rely on pressure constantly in breathing, weather, and engineered systems. The explanation does not need to feel mechanical. The connection itself can remain quietly understood. As pressure settles, variation can appear without disruption. Imagine the same gas expanding into a larger space, thinning as it spreads. The factual idea here is that atomic motion causes gases to diffuse and mix spontaneously. Atoms move from regions of higher concentration to lower concentration until evenly distributed. This occurs without direction or preference. The significance lies in inevitability. Mixing does not require effort or instruction. From where you are, air composition remains stable precisely because of this constant motion. You don't need to notice diffusion happening. Its quiet persistence is enough. With motion, probability, and balance now intertwined, attention can pause without stopping. Imagine the environment once more as it is now, unchanged, supported by countless small motions working together. The core fact here is that macroscopic calm often rests on microscopic activity. Stillness at human scale usually reflects balanced motion rather than absence of movement. This balance is dynamic, not fragile. The significance is steadiness. Activity does not imply instability. As an observer, you live within that balance continuously, without needing to manage it. For now, the idea can remain gently open, ready to continue without resolution. The sense of balanced motion remains present, with calm at the surface supported by quiet activity underneath. Nothing from before needs to be emphasized again. You might imagine a clear glass of water sitting still on a table. Its surface is smooth, unbroken, offering no hint of motion. The central fact here is that liquids appear stable even though their atoms are constantly rearranging. In a liquid, atoms remain close together, but they continuously move past one another, changing neighbors over time. This motion is constrained, not free. Forces keep the atoms near, even as they shift positions. Why this matters is subtle. Liquids can flow and adapt shape without losing cohesion. As an observer, you experience this as softness, fluidity, and continuity. The idea does not require visualization of individual atoms. The surface calm is enough to let the fact rest gently. With liquid motion in mind, boundaries can appear softly without becoming rigid. Picture the edge of that water against the glass, clearly defined yet flexible. The factual idea here is that surface tension arises from atomic interactions at boundaries. Atoms at a surface experience different forces than those inside, creating a tendency to minimize surface area. This effect is measurable and consistent across liquids. The significance lies in explanation. Droplets form spheres, insects can rest on water, and surfaces curve gently. From your position, these effects appear ordinary and intuitive. You don't need to calculate forces. The visible outcome carries the explanation quietly forward. With boundaries acknowledged, cohesion can remain present without tightening focus. Imagine water molecules staying together as they move, resisting separation. The single fact here is that intermolecular forces hold atoms and molecules together in liquids. These forces are weaker than chemical bonds, but strong enough to maintain structure. They act continuously and without interruption. This matters because it explains why liquids do not fall apart into gases under ordinary conditions. As an observer, you rely on this cohesion in everything from drinking water to weather patterns. The idea can remain as a quiet connective force, steady and unobtrusive. As cohesion settles, contrast can appear gently, without opposition. Picture the same water now warming slowly, becoming more active. The factual focus here is that increasing temperature weakens the effective hold of intermolecular forces. As atomic motion increases, atoms overcome these attractions more easily, eventually transitioning to gas. No bonds are broken at the atomic core, only interactions change. The importance lies in continuity. Phase transitions follow gradual shifts in energy, not sudden changes in identity. From where you are, boiling and evaporation feel familiar and predictable. The idea can remain calm, aligned with experience rather than explanation. With gas now present again, space can widen without becoming abstract. Imagine air filling a room completely, touching every surface. The single fact here is that gases expand to fill available volume because of atomic motion. Without strong attractive forces to keep them close, atoms move freely until evenly distributed. This behavior follows statistical rules rather than intent. This matters because it explains why gases spread, mix, and equalize naturally. As an observer, you breathe in air that remains evenly available without effort. The idea can remain as a quiet assurance of availability and balance. As expansion settles, lightness can enter without emphasis. Picture a balloon rising slowly, supported by the air around it. The factual idea here is that differences in atomic mass and motion contribute to buoyancy. Gases with lighter atoms or faster motion can exert less downward force, allowing objects to rise. This principle applies across fluids, not just air. The significance lies in connection. Atomic properties scale into large, visible effects. From your perspective, buoyancy feels simple, even playful. The explanation does not need to be held tightly. The effect itself carries the meaning. With fluids, motion, and balance now interwoven, attention can pause without closing. Imagine the room again, unchanged, filled with air and quiet activity. The core fact here is that fluid behavior reflects collective atomic motion rather than individual actions. No single atom determines flow, pressure, or stability. Patterns emerge only through numbers. The significance is gentleness. Large effects arise without central control. As an observer, you live within these collective patterns constantly, without directing them. For now, the idea can remain open, steady enough to continue without conclusion. The sense of collective motion remains in place, with large patterns quietly supported by countless small movements. Nothing from before needs to be restated. You might imagine a wide, open landscape, perhaps a plain or shoreline where nothing appears to be happening quickly, yet subtle changes continue everywhere. The central fact here is that atoms respond to forces without awareness or intent. Gravity, electromagnetic forces, and pressure act on atoms consistently, producing motion and structure without decision-making. This behavior is automatic. Atoms do not choose responses. They follow physical laws precisely. Why this matters is grounding. Complex outcomes do not require intelligence at the smallest scales. As an observer, you benefit from systems that function reliably without guidance. The The idea can remain calm, allowing causation to feel steady rather than dramatic. With force response quietly present, order can appear without contradiction. Picture a crystal forming slowly, its shape emerging without planning. The factual idea here is that atoms can arrange themselves into highly ordered structures. In solids like crystals, atoms settle into repeating patterns that minimize energy. This ordering is not imposed externally, it emerges from interactions and constraints. The significance lies in explanation. Regular shapes and symmetry arise naturally from atomic behavior. From your perspective, crystals appear static and precise, even though their formation was gradual. You don't need to track the process. The presence of order alone can remain quietly understood. With order acknowledged, variation can appear gently alongside it. Imagine imperfections within a crystal, small irregularities that do not disrupt the whole. The single fact here is that real materials contain atomic defects. Missing atoms, misalignments, and substitutions occur naturally within structures. These defects are not failures. They influence electrical, mechanical, and optical properties. This matters because perfection is not required for function. Useful behavior often depends on imperfection. As an observer, you rely on materials engineered with controlled defects, even if you never see them. The idea can remain neutral, descriptive rather than evaluative. As defects settle into view, movement can return quietly within solids. Picture atoms vibrating gently in place, never fully still. The factual focus here is that even solid atoms vibrate continuously. Absolute stillness occurs only at theoretical absolute zero, which is never fully reached. These vibrations increase with temperature and decrease as cooling occurs. The importance lies in continuity. Solids are dynamic at small scales, not frozen arrangements. From where you are, solidity feels complete and unmoving. That contrast between feeling and structure can remain softly present without tension. With vibration acknowledged, sound can enter without becoming loud. Imagine a faint vibration traveling through a surface, spreading outward. The single fact here is that sound is transmitted through atomic vibrations. In solids, liquids, and gases, sound waves move as atoms pass motion along to neighbors. No atom travels with the wave. Only energy and motion propagate. This matters because it links sensation to structure. Hearing depends on atomic cooperation. As an observer, you experience sound as information, not as moving matter. The explanation can rest quietly beneath the experience. With sound now present, limits can appear gently. Picture the same vibration attempting to pass through empty space, then fading. The factual idea here is that sound cannot travel through a vacuum. Without atoms to transmit vibration, sound has no medium. This is not a limitation of hearing, but of structure. The significance lies in contrast. Some phenomena require matter, others do not. From your perspective, silence in space is a consequence of absence, not stillness. The idea can remain as a simple boundary, quietly defined. With vibration, structure, and absence now aligned, attention can pause again without stopping. Imagine the environment once more as it is now, solid, quiet, and reliable. The core fact here is that many familiar experiences arise from collective atomic behavior. Sound, solidity, and order are emergent, not fundamental. This emergence does not require oversight. It happens continuously. The significance is steadiness. Complexity does not imply fragility. As an observer, you live within these outcomes without needing to resolve their origins. For now, the idea can remain open, gently carrying forward without conclusion. The sense of emergence remains quietly present, with familiar experiences resting on collective behavior beneath awareness. Nothing needs to be restated or reinforced. You might imagine a dimly lit room again, still and ordinary, where objects simply remain where they are. The central fact here is that electrical phenomena arise from the movement of electrons between atoms. When electrons shift position or flow through materials, electric effects appear. This movement does not involve whole atoms travelling far. It is the behaviour of outer electrons that matters. Why this matters is explanatory. Electricity is not a separate substance, but a pattern of atomic behaviour. As an observer, you interact with electricity constantly through light, devices, and communication without seeing the electrons involved. The idea can remain calm, grounding modern experience in simple motion. With electrical movement present, pathways can appear gently without narrowing focus. Picture a wire resting quietly, inactive until connected. The factual idea here is that some materials conduct electricity because their atoms allow electrons to move freely. In metals, electrons are not tightly bound to individual atoms, enabling current flow. This property arises from atomic structure, not from added features. The significance lies in predictability. Conductors and insulators behave consistently based on atomic arrangement. From your position, this reliability allows safe and controlled use of electrical systems. You do not need to follow the electrons. Trust in the material is enough. As conduction settles, resistance can appear softly without opposition. Imagine current moving through a narrow path, slowing slightly as it goes. The single fact here is that electrical resistance results from interactions between moving electrons and atomic structure. Collisions and scattering convert some electrical energy into heat. Resistance is not failure, it is an inherent property of materials. This matters because it explains energy loss and heating in electrical systems. As an observer, you experience resistance indirectly, through warmth or limited current. The idea can remain descriptive, neither positive nor negative, simply present. With resistance acknowledged, magnetism can enter without surprise. Picture a compass needle settling into alignment, quietly responsive. The factual focus here is that magnetism arises from moving electric charges and intrinsic atomic properties. Electron motion and spin produce magnetic fields. This connection between electricity and magnetism is fundamental and well established. The importance lies in unity. Separate seeming forces share a common origin at the atomic level. From your perspective, magnets appear stable and predictable. Their behavior can remain quietly understood without tracing every interaction. With magnetic effects present, interaction at a distance can feel less abstract. Imagine invisible lines shaping space around an object, without touch. The single fact here is that atomic scale forces can act across empty space. Electric and magnetic fields influence particles without direct contact. These fields are measurable and consistent. This matters because it explains non-contact interactions in nature and technology. As an observer, you benefit from these forces in communication, navigation, and sensing. The idea can remain calm, even as space itself becomes active. As fields rest quietly, control can appear without dominance. Picture a switch closing a circuit, allowing flow to begin. The factual idea here is that human-designed systems guide atomic behavior without altering atomic rules. Circuits, motors, and devices channel electrons using structure rather than force. Atoms still follow the same laws, only pathways change. The significance lies in partnership. Technology works by cooperating with atomic behavior. From where you are, devices respond predictably without needing oversight. That cooperation can remain quietly present. With electricity and magnetism now aligned, attention can pause without ending. Imagine the environment again, softly lit, supported by invisible flows. The core fact here is that modern technologies rely on consistent atomic behavior. Their reliability depends on electrons behaving the same way everywhere, every time. This consistency is tested continuously and confirmed. The significance is trust. Complex systems rest on simple, stable rules. As an observer, you live within that trust daily without needing to examine it. For now, the idea can remain open, ready to continue without resolution. The sense of technological trust remains quietly present, with invisible flows supporting ordinary experience. Nothing from before needs to be reinforced. You might imagine the same environment again, perhaps a room at night, lit gently and without drama. The central fact here is that light is produced when atoms release energy. When electrons move from higher to lower energy levels, the excess energy is emitted as light. This emission follows precise rules. Each transition corresponds to a specific energy difference. Why this matters is clarity. Light is not separate from matter. It is a direct expression of atomic behavior. As an observer, you encounter light constantly from lamps, screens, and the sky. The idea can rest quietly, allowing illumination to feel familiar rather than mysterious. With light present, colour can appear softly without emphasis. Picture a spectrum spreading gently from deep red to violet. The factual idea here is that different colours of light correspond to different energy levels. Higher energy transitions produce shorter wavelengths, while lower energy transitions produce longer ones. This relationship is fixed and measurable. The significance lies in explanation. Colour is not subjective at its source, it reflects specific atomic processes. From your position, colour becomes perception only after this atomic origin. You do not need to track wavelengths. The connection alone can remain quietly understood. As colour settles, absorption can enter without contrast. Imagine light passing through a material, some wavelengths fading away. The single fact here is that atoms absorb light by taking in energy that matches their internal transitions. Absorbed light raises electrons to higher energy states. This process is selective, not general. This matters because it explains why materials appear coloured or transparent. As an observer, you see objects as they reflect or absorb light, not as they emit it. The explanation can remain beneath perception, steady and unobtrusive. With absorption present, reflection can follow gently. Picture light bouncing from a surface, unchanged in colour. The factual focus here is that reflection occurs when light interacts with atomic electrons without being absorbed. The light's energy remains intact and is redirected. This interaction depends on surface structure and electron behaviour. The importance lies in familiarity. Mirrors, water surfaces, and polished metals rely on this process. From where you are, reflection feels immediate and reliable. The atomic detail can remain quietly in the background. As reflection settles, transparency can appear without narrowing focus. Imagine light passing through glass almost unhindered. The single fact here is that transparent materials have atomic structures that do not readily absorb visible light. Their electrons lack energy transitions matching visible wavelengths. This allows light to pass through with minimal loss. This matters because it explains windows, lenses, and optical clarity. As an observer, you look through transparency without considering its cause. The idea can remain calm, aligned with everyday experience. With light behavior established, interaction can broaden without escalating. Picture multiple light sources overlapping, blending softly. The factual idea here is that light can interact with matter in predictable ways across scales. Scattering, refraction, and absorption all arise from atomic responses to electromagnetic waves. No new principles are introduced at larger scales. The significance lies in coherence. Optical behavior reflects consistent atomic rules. From your perspective, vision and imaging rely on this steadiness. You're not required to analyze it. The reliability is enough. With light, color, and matter now aligned, attention can pause again without closing. Imagine the environment once more, illuminated and stable, quietly understandable. The core fact here is that perception depends on atomic interactions occurring before awareness. Sight begins at the level of electrons long before experience forms. This sequence is constant and automatic. The significance is calm continuity. Experience rests on processes that do not require attention. As an observer, you receive the outcome without needing to manage the cause. For now, the idea can remain open, gently ready to continue. The sense of perception resting on quiet processes remains in place. With awareness arriving only after deeper interactions have already occurred, nothing needs to be reinforced. You might imagine a familiar scene again, perhaps daylight entering a room ordinary and unremarkable. The central fact here is that atoms interact with light without awareness or choice. When light encounters matter, atomic electrons respond according to fixed physical rules. There is no interpretation at this level, only interaction. These responses occur instantly and consistently. Why this matters is grounding. The foundations of perception are mechanical rather than interpretive. As an observer, meaning arrives later, layered atop these interactions. The idea can remain quiet, allowing cause and experience to feel gently separated. With interaction resting calmly, delay can appear without tension. Picture a signal travelling, not hurried, but steady and assured. The factual idea here is that atomic interactions occur far faster than human perception. Light absorption, electron transitions, and signal transmission happen in fractions of a second, long before awareness registers them. This timing difference is measurable and consistent. The significance lies in trust. You experience a seamless world because atomic processes complete their work before sensation begins. From where you are, response feels immediate, even though layers of activity precede it. You do not need to follow the timing. The smoothness is enough to let the idea settle. As timing fades into the background, scale can shift gently again. Imagine a sensor, perhaps a camera or detector, quietly responding to incoming light. The single fact here is that human-made instruments detect atoms and atomic effects indirectly. Devices measure energy, charge, or motion produced by atomic interactions rather than atoms themselves. These measurements are translated into signals humans can interpret. This matters because direct atomic observation is rare. Knowledge often comes through layered inference. As an observer, you trust instruments to extend perception beyond natural limits. The idea can remain calm, highlighting cooperation between human design and atomic behavior. With measurement present, limits can appear softly, without frustration. Picture a boundary where clarity gives way to uncertainty. The factual focus here is that there are fundamental limits to how precisely atomic properties can be known simultaneously. Certain pairs of measurements, like position and momentum, cannot both be exact. This is not due to poor tools, but to physical law. The importance lies in acceptance. Precision has boundaries built into nature itself. From your perspective, these limits do not disrupt everyday experience. They remain quietly relevant only when probing the smallest scales. With limits acknowledged, stability can return without contrast. Imagine an atom persisting unchanged despite uncertainty around it. The single fact here is that uncertainty at atomic scales does not undermine macroscopic stability. Large collections of atoms average out variability, producing reliable outcomes. This averaging is statistical, not intentional. This matters because it preserves predictability. Uncertainty remains contained. As an observer, you live in a world where objects stay put and processes repeat. The idea can rest as reassurance without argument. As stability settles, complexity can appear gently. Picture layers building, not stacked deliberately, but emerging from repetition. The factual idea here is that complex systems arise from simple atomic rules repeated many times. No new atomic laws are introduced as systems grow more intricate. Complexity is cumulative rather than invented. The significance lies in continuity. The same foundations support molecules, materials, and organisms. From where you are, complexity feels rich but not fragile. The explanation can remain beneath experience, steady and sufficient. With complexity resting quietly, attention can pause again without stopping. Imagine the world as it is now, unchanged, quietly functioning at every scale. The core fact here is that atomic behavior remains consistent even as systems become elaborate. Growth does not alter the underlying rules. This consistency is confirmed across observation and experiment. The significance is steadiness. Expansion does not require revision. As an observer, you benefit from this reliability without needing to confirm it. For now, the idea can remain open, gently carried forward without closure. The sense of steadiness remains quietly present, with complexity resting comfortably on simple, unchanging rules. Nothing from before needs to be restated. You might imagine a long-lived object, a stone, a piece of wood, a familiar structure that has remained mostly unchanged through many seasons. The central fact here is that atoms do not have memory of past interactions. An atom behaves the same way regardless of where it has been or what it has previously bonded with. Its behavior depends only on its current state and surroundings. Why this matters is neutrality. Atoms carry no history forward to influence future behavior. As an observer, you encounter materials shaped by history, even though their atoms themselves remain indifferent. That separation between material history and atomic neutrality can remain quietly in view. With neutrality resting calmly, repetition can appear without monotony. Picture the same process occurring again and again, yielding the same result each time. The factual idea here is that atomic interactions are repeatable under identical conditions. When the same atoms meet under the same circumstances, they behave the same way. This repeatability is the basis of experimental science. The significance lies in trust. Knowledge accumulates because outcomes are stable. From your perspective, this allows expectations to form without constant verification. You do not need to witness the repetition. The reliability itself is enough to let the idea settle. As repetition becomes familiar, symmetry can enter gently. Imagine patterns that mirror themselves, balanced and even. The single fact here is that many atomic structures exhibit symmetry. Atoms and molecules often arrange themselves in patterns that repeat evenly in space. This symmetry arises from energy minimization rather than design. This matters because symmetry influences physical properties like strength, conductivity, and optical behavior. As an observer, you notice symmetry visually without tracing its origin. The explanation can remain beneath perception, quiet and sufficient. With symmetry present, asymmetry can follow without conflict. Picture a structure that's mostly regular, with small deviations. The factual focus here is that slight asymmetries at the atomic level can produce significant effects. Small differences in arrangement can lead to different chemical behavior or biological activity. These effects are measurable and consistent. The importance lies in sensitivity. Large outcomes can follow from small variations. From where you are, such differences often appear as distinct properties or functions. The idea can remain descriptive without assigning importance beyond consequence. As variation settles, direction can appear softly. Imagine a process that favors one outcome over another, without intention. The single fact here is that some atomic processes have preferred directions due to energy gradients. Reactions tend to proceed toward lower energy configurations. This tendency is statistical, not purposeful. This matters because it explains why certain changes occur naturally while others require added energy. As an observer, you experience this as effort versus ease. The atomic origin of that difference does not need to be emphasized to be present. With energy gradients present, boundaries can soften again. Picture atoms exchanging energy quietly, never fully isolated. The factual idea here is that atoms are influenced by their surroundings at all times. Nearby atoms, fields, and temperatures shape behavior continuously. No atom exists in complete isolation under ordinary conditions. The significance lies in connection. Context always matters. From your perspective, environments shape outcomes without being noticed directly. The idea can rest as a gentle reminder of interdependence without emphasis. With influence and neutrality now aligned, attention can pause without stopping. Imagine the same long-lived object again, unchanged in appearance, quietly supported by countless neutral interactions. The core fact here is that stability at human scales depends on atomic indifference rather than adaptation. Atoms do not adjust behavior to maintain stability. Stability emerges from repetition. This emergence is automatic. The significance is calm reassurance. Reliability does not require awareness. As an observer, you live within that reliability constantly. For now, the idea can remain open, ready to continue without conclusion. The sense of reliability remains quietly in place, supported by repetition rather than adjustment. Nothing from before needs to be restated. You might imagine a familiar object once more, perhaps a chair or a doorway, something that simply remains where it is meant to be. The central fact here is that atomic behavior does not scale with intention or purpose. Atoms do not behave differently because they are part of tools, organisms, or natural landscapes. Their actions are the same in all contexts. This uniformity is not imposed, it is intrinsic. Why this matters is neutrality. Meaning exists at higher levels, not at the atomic one. As an observer, you move through meaningful spaces built from components that do not share that meaning. That separation can remain quietly present without needing interpretation. With neutrality resting calmly, boundaries between living and non-living can soften. Picture a leaf and a stone resting side by side, different in form, similar in substance. The factual idea here is that the same types of atoms exist in both living and non-living matter. Carbon, hydrogen, oxygen, and other elements participate in rocks, air, water, and organisms alike. No special atoms are reserved for life. The significance lies in continuity. Life uses existing matter rather than requiring new kinds. From your perspective, this makes the boundary between living and non-living feel gradual rather than sharp. The idea can remain descriptive without drawing conclusions. As continuity settles, organization can appear without emphasis. Imagine atoms arranged into repeating units, then layered into larger patterns. The single fact here is that living systems organize atoms into highly specific arrangements. Biological molecules rely on precise atomic positioning to function correctly. This precision arises from chemistry, not intention. This matters because function depends on structure at small scales. As an observer, you benefit from biological reliability without tracking atomic placement. The explanation can remain quietly beneath experience. With biological organization present, fragility can appear gently. Picture a structure that works well within certain conditions, but not beyond them. The factual focus here is that biological atomic arrangements are sensitive to changes in environment. Temperature, pH, and radiation can disrupt structure by altering atomic interactions. This sensitivity is measurable and consistent. The importance lies in limitation. Precision enables function but reduces tolerance. From where you are, this sensitivity appears as vulnerability rather than instability. The idea can remain neutral, descriptive rather than evaluative. As sensitivity settles, regulation can follow without control. Imagine conditions held within a narrow range, not by command but by balance. The single fact here is that living systems maintain internal conditions through continuous atomic exchanges. Homeostasis relies on ongoing chemical reactions and transport processes. Atoms move constantly to preserve overall stability. This matters because balance is active rather than static. As an observer, your body maintains itself without conscious oversight. The atomic basis of that balance does not need attention to function. With regulation present, breakdown can appear softly, without alarm. Picture the same system gradually losing balance over time. The factual idea here is that when atomic processes drift beyond regulated ranges, biological systems fail. Loss of structure or reaction control leads to dysfunction. This follows physical law rather than exception. The significance lies in explanation. Failure reflects limits, not error. From your perspective, aging and illness appear as complex phenomena. Their atomic roots can remain quietly acknowledged. With life, neutrality, and limitation now aligned, attention can pause again without stopping. Imagine the environment once more as it is now, containing both living and non-living forms without distinction at the smallest scale. The core fact here is that atomic rules apply equally everywhere. Regardless of outcome, life does not modify them, it operates within them. This consistency is complete. The significance is steadiness. Rules do not adapt to purpose. As an observer, you exist within that steadiness continuously. For now, the idea can remain open, gently ready to continue. The sense of steadiness from before remains present, with atomic rules applying evenly across all contexts. Nothing needs to be emphasized again. You might imagine the same ordinary setting one last time: a room, a landscape, a familiar place that feels settled and complete. The central fact here is that atoms do not strive toward outcomes. They do not seek stability, complexity, or persistence. They follow physical laws moment by moment, without reference to past or future states. This absence of intent is not a limitation. It is a defining feature of atomic behavior. Why this matters is grounding. Order and continuity arise without purpose at the smallest scales. As an observer, you encounter result structures, systems, histories, without needing to attribute motivation beneath them. The idea can rest quietly, allowing causation to feel steady rather than directed. With the absence of intent resting calmly, accumulation can appear without planning. Picture layers forming over time, each one added without awareness of the whole. The factual idea here is that long-term structures arise from repeated atomic interactions over time. Mountains, atmospheres, oceans, and materials emerge from countless small processes accumulating gradually. No single interaction determines the outcome. Time and repetition do the work. The significance lies in patience. Large-scale features reflect duration rather than force. From your perspective, these structures feel permanent, even though they are the result of ongoing atomic motion. The idea does not require scale to be grasped fully. Duration alone can remain quietly present. As accumulation settles, persistence can appear gently, without emphasis. Imagine an object that remains recognizable even as its components subtly change. The single fact here is that macroscopic identity can persist even as individual atoms are replaced. Objects, systems, and organisms maintain form through structure rather than fixed components. This replacement occurs continuously and without disruption. This matters because stability does not require sameness at the smallest level. Pattern matters more than material. As an observer, you recognize continuity without tracking atomic turnover. The explanation can remain beneath experience, calm and sufficient. With persistence established, limits can return softly without concern. Picture a system that holds together well, but not indefinitely. The factual focus here is that atomic processes are indifferent to human timescales. They operate over ranges that can be far shorter or far longer than individual experience. Decay, transformation, and rearrangement occur regardless of observation. The importance lies in neutrality. Change is not accelerated or slowed by attention. From where you are, some changes feel sudden, others imperceptibly slow. The atomic pace does not adjust. The idea can remain quietly descriptive. As time settles into the picture, simplicity can reappear without reduction. Imagine returning to the smaller scale again, without urgency or focus. The single fact here is that all observable material complexity arises from a limited set of atomic building blocks. A small number of elements combine and recombine to produce the full range of physical forms encountered. This economy is not imposed, it is a consequence of stable atomic properties. This matters because richness does not require excess. Variety emerges from combination. As an observer, you live within that variety without needing to catalogue it. The idea can rest as a quiet sufficiency at the foundation of matter. With simplicity present, understanding can loosen without disappearing. Picture knowledge not as a finished structure, but as a gently held outline. The factual idea here is that atomic science remains incomplete without being unstable. Models improve, measurements refine, but core behaviours remain consistent across generations of study. Uncertainty does not imply unreliability, it reflects ongoing refinement. The significance lies in humility. Knowledge grows without overturning its foundations. From your perspective, understanding can deepen without needing to resolve everything. The idea can remain open, neither fixed nor fragile. With openness now aligned with steadiness, attention can finally rest without closing the subject. Imagine the world once more as it is now, ordinary, intact, quietly supported at every scale. The core fact here is that atoms continue behaving exactly as they do, regardless of whether they are observed or considered. Their rules do not depend on awareness. This consistency does not require confirmation, it simply persists. The significance is calm continuity. The world holds together without needing supervision. As an observer, you're free to notice this or let it pass by. For now, the idea can remain unfinished, present without demand, gently complete in its incompleteness. There's nothing here that needs to settle into memory or resolve into a clear shape. The ideas can remain scattered, or loosely connected, or simply present in the background. You may feel alert, or a little distant, or exactly the same as before, and all of that fits comfortably within what we've explored. Atoms will continue behaving as they always have, regardless of how closely they're considered, or whether they're considered at all. If any part of this stays with you, it can do so without effort, and if nothing stays, that's fine too. The world beneath things keeps going either way, quietly, without asking for attention.